Hello everyone, welcome to this lecture on shrinkage in metal casting processes. Today we are going to explore a crucial topic in foundry engineering that significantly affects the quality of cast components. By the end of this video, you will understand what shrinkage is, its types, causes, and most importantly, how we can minimize it. So let's dive right in. Shrinkage is the reduction in the volume of a metal as it cools and solidifies during the casting process. Metals expand when heated and contract when cooled. This contraction is natural, but in casting it can lead to defects such as voids, cavities, or even cracks in final process. This goes by the definition as shrinkage in metal casting refers to the reduction in volume that occurs as molten metal cools and transition from a liquid to a solid state. This phenomenon happens because metals contract when they lose heat, which can lead to the formation of voids, cavities. These are the voids that are shown in this picture. Cavities or cracks in the final casting if not properly managed. You can look at the voids and cavities that occurred as it was not properly managed. There is some significance of shrinkage. Impact on product quality. Shrinkage can lead to defects like porosity, cavities, and cracks, which weaken the casting, reduce its structural integrity, and compromise its performance. Design considerations. To ensure a defect-free casting, mold designs often include features like risers, feeders, and shrinkage allowances to compensate for volume reduction during solidification. Manufacturing efficiency. Managing shrinkage effectively reduces the need for rework, repairs, or rejection of cast parts, thus improving production efficiency and reducing costs. Material utilization. Properly accounting for shrinkage helps minimizing material wastage and optimize the amount of metal poured into the mold. Economic significance. Shrinkage-related defects can lead to significant financial losses, especially in industries like aerospace, automotive, and heavy machinery, where precision and reliability are critical. Technology and advancements. The study and control of shrinkage have driven innovations in simulation softwares, mold design, and material science to predict and prevent defects in modern casting processes. Shrinkage mainly occurs due to three stages, like liquid shrinkage, solidification shrinkage, solid shrinkage. By liquid shrinkage, we can understand that the reduction in volume when molten metal cools but is still liquid. Solidification, the contraction during the phase change from liquid to solid. Solid shrinkage, the reduction in volume after the metal has completely solidified. We can understand by this flowchart. Liquid shrinkage reduction in volume while still liquid. It occurs while metal is molten. Solidification shrinkage contracts during liquid to solid phase change. It occurs as metal solidifies. Solid shrinkage reduction in volume after solidification. It occurs after solidification. Each of the stage plays a role in creating defects if not properly addressed. So let's move on to the next slide. Let's break down the mechanism of shrinkage. When molten metal is poured into a mold, it cools and solidifies. Implications of shrinkage. Shrinkage can create defects like voids and cracks in the casting. Understanding these implications helps in designing better molds and improving cooling techniques. If you go through the mechanism of this, then initially the metal loses heat rapidly, causing liquid shrinkage. You can relate it with the earlier flowchart that I have given. During solidification, the outer layer solidifies first, forming a shell. The inner steel molten metal contracts, leaving voids or cavities. Finally, as the casting continues to cool, solid shrinkage can occur, causing the casting to pull away from the mold well. These defects are usually most noticeable in thicker sections of a casting where cooling is uneven. This was about the mechanism of shrinkage. Shrinkage defects can be classified into several types. This table summarizes the main types of defects caused by shrinkage in metal casting. Understanding this will aid in addressing potential issues. Shrinkage cavity is one of the defects, which is a large void typically found in thick sections. It appears like a visible hollow area in the product. The second type of defect is microporosity, which is small dispersed voids throughout the metal. It appears like a tiny holes visible on surface of the metal. The third type of defects is hot tears, cracks formed during solidification. It appears like surface cracks evident on casting. Understanding these defects helps in designing process to minimize them, to minimize these defects. The extent of shrinkage is influenced by several process parameters like pouring temperature. Higher pouring temperature can result in increasing shrinkage. Optimal temperatures must be maintained to reduce defect risk. Cooling rate. Faster cooling leads to uneven shrinkage, which can cause defects. Controlled cooling is crucial for high quality castings. Mold materials and design. The choice of mold material affects cooling rates and shrinkage. Proper design ensures uniform heat distribution. By optimizing these parameters, we can significantly reduce shrinkage defects. It's about the applications. Why is understanding shrinkage so important? Castings are used in industries like automotive, aerospace, and construction components, such as engine blocks, turbine blades, and gears require high precision and minimal defects. By understanding and controlling shrinkage, we can ensure higher quality and durability of these critical parts. Industries impacted by shrinkage controls are like understanding and effectively controlling shrinkage is vital across various industries. For example, the automotive and aerospace sectors rely on precision cast components to ensure safety and functionality. While shrinkage is a challenge, controlling it has its own advantages and disadvantages. From the disadvantages of managing shrinkage, we can say that it has increased costs of risers and feeders. Secondly, we can say that more complex mold designs required, demands for rigorous inspection and quality control. These are the disadvantages of managing a shrinkage. Let's move on to advantages. It says about improved structural integrity in castings, enhanced surface finish with fewer defects, greater production efficiency through optimized process. These are the advantages and even disadvantages while managing a shrinkage. In recent years, advancement in technology have led to innovative methods for controlling shrinkage. Like future trends in shrinkage control are like simulation softwares. Tools like ANSYS and Procast predict shrinkage and optimize mold designs. This is an example of ANSYS analysis. AI and automation. You can use AI also. AI helps in monitor and adjust processes parameters in real time. We can also change the materials like by using advanced materials like alloys with lower shrinkage rates. These trends are making castings more efficient and reliable than ever before. We've come to the end of this lecture. These are the key takeaways. These are the key takeaways. Let's wrap up. Shrinkage is a natural contraction during metal cooling that leads to defects if uncontrolled. It can be managed by optimizing parameters like temperature, cooling rate, and mold design. With advancements in technology, we are finding better ways to predict and prevent shrinkage. So that's all. Thank you for watching.